We will now begin today's program with an introduction from Carnegie President Eric Isaacs.
Good afternoon. We're really delighted to welcome you to our program this afternoon, where we will be featuring Alycia Weinberger, who is an astronomer at Earth and Planets Laboratory here in Washington, D.C. Alycia is here today to talk about an important new instrument that she and her colleagues are developing that will specifically go on telescopes at Carnegie's Las Campanas Observatory in Chile. Our Las Campanas Observatory is high in the Atacama Desert and offers superb seeing, largely due to a few reasons. One is that it's an extremely dry, high desert. It has very little annual cloud cover and also almost no rainfall and very minimal light pollution. It's home to many of our telescopes, our twin 6.5-meter Magellan telescopes, as well as the Swope and DuPont telescopes. And you'll hear more about that in Alycia's talk today, how she will use those. It's also going to be the future home of the Giant Magellan Telescope, which is currently under construction there. When completed, this telescope, the Giant Magellan Telescope, will be an extremely large 24-meter ground-based telescope. This makes it one of the largest telescopes in the world and will enable serious breakthroughs in our understanding of the universe, in particular in areas like identifying planets, distant worlds that could be capable of hosting life. And Alycia will be discussing the connection between her instrument and this exciting new direction of discovery. Suffice it to say that that in general, novel instruments, novel instrumentation, they're all a critical component for discovery in astronomy. As with all scientific fields, when you develop a new instrument, especially as unique as the one Alycia will tell us about, you're bound to discover exciting new things. And the instrument that Alycia is here to speak about today is called MagNIFIES, for what it stands for, and she'll tell you more, Magellan's Near-Infrared 5-Band Immersion Grating Efficient Spectrograph, and she is co-developing this with UT Austin. And we were excited, in fact, to learn just recently that the project is receiving funding from the Heising-Simons Foundation that will help us advance this project much more rapidly. When it's completed, this instrument will be in a class by itself. It'll be the largest. It'll be able to take the largest simultaneous spectra with very high resolution anywhere in the world of things outside of this world. And today, Alycia will teach us about her instrument that will enable such breakthroughs. In particular, Alicia's interest is in studying young stars and the protoplanetary or rotating disks of gas and dust that surround them, which provide the raw materials from which planets like the Earth, like Jupiter and Mars in our own solar system, planets are born. She's a specialist in searching for new and known planetary systems in these protoplanetary disks in order to better understand the conditions that exist for planetary formation and how the elements of the disk, the components of the disk, elements, molecules, rocks, everything, including the composition and distribution of these disk materials, shapes the planetary system's architecture as it evolves. The instrument MagNIFIES will also help astronomers to better understand the molecular makeup of these atmospheres on exoplanets once they form, a knowledge which is crucial to developing an understanding of what makes another world potentially capable of hosting and sustaining life. It is, in fact, one of the most important questions. It's not likely we're visiting any even nearby planets outside of our solar system. So one of the most important questions is what can we learn from their atmospheres about what might be on the planet's surface, such as life, or even in the atmosphere, such as life. And this instrument MagNIFIES will help us make significant inroads on that very important question. Alycia joined us at Carnegie 20 years ago in 2001, following a postdoctoral position in astronomy and astrobiology at UCLA. And she earned her PhD in physics from Caltech, a bachelor's degree in the same, which is astrophysics from the University of Pennsylvania. She was a member of the inaugural class of fellows of the American Astronomical Society just last year in 2020, and is a recipient of the Society's Annie Jump Cannon Award. So please join me in welcoming Dr. Alycia Weinberger. Alycia?
Great, thank you very much, Eric. So thanks to all the participants for joining us. I'm excited to tell you about an instrument that will magnify our knowledge of planet formation and exoplanets. Its design, development, and construction are a collaboration, as Eric said, with Daniel Jaffe at the University of Texas. also with the Korea Astronomy and Space Science Institute and the Giant Magellan Telescope, as well as Carnegie's Earth and Planets Laboratory, where I work, and our Carnegie observatories. And as you said, we have some recent support from the Heising-Simons Foundation for buying some key components. So I'm going to motivate why I want to build this instrument by sharing some of the scientific questions that intrigue me in understanding how planets form and what exoplanet atmospheres are made of. Then I'm going to explain a little bit about infrared spectroscopy and why it's an essential tool to answering these questions. Third, I'm going to show how MagNIFIES is so special. And I'll wrap up by showing you a bit more about how we can use it to study exoplanets, but I also look forward to your questions in this virtual conversation. So we have a timeline of what happened in our own solar system. We can't watch a system evolve for 4.567 billion years. We have to go out and find examples of stars at different ages and look at them to see what's happening. So this shows what happened in our solar system over time. But the really key thing that I want you to keep in mind today is that in the first few million years, not only did objects the size of Mars formed, but probably planets as big as Jupiter formed as well. And so what was happening very early on in the creation of our solar system sets the time period for when we want to look at other planetary systems. And we can see those disks of dust and gas around other planetary systems that are the birthplaces and the interaction places for planets. So for example, this is the disk around the star TW Hydra, which is the closest example of a planet-forming disk that we have to the sun. And so I and many other people have studied it for many years. And deep in this black hole, which isn't really a black hole in the astronomical sense, but it's a hole in what we're able to see, that is the scale of the inner part of our solar system out to the distance of Earth and the distance of Jupiter is all very much here in the center. Now we think, as you can see, there's a gap in this disk. Exciting things might be happening further out as well. But we want to probe these very close locations and find out what they're made out of, where that gas and dust is going, how it interacts with any planets forming in the system, to understand how the great variety of planets that we know came to be. So what types of planetary systems form in different disks? What are those atmospheres of those planets made out of? We know now from a census of planets, and these are all the confirmed planets that we know of that have a measured radius, plotted as a function of their orbital period. And you can see the planets in our solar system that we know and love here. And you'll see that the vast majority of planets we know about are nothing like anything that we have in our solar system. They're these super Earths and mini Neptunes, planets a couple times the size of the Earth. So this is one Earth, right, in size. This is two Earth sizes, and much closer to their stars than even Mercury is to our sun. So how did these planets come to be? Were there particular kinds of disks they formed in? How did our solar system come to be? Do we have to form in a special kind of disk? These are all questions that motivated the concept for a new instrument that could study both the inner parts of disks and exoplanet atmospheres. And that concept is now about 15 years old and started with Dan Jaffe at the University of Texas as a concept for the Giant Magellan Telescope. So here's a artist's conception of what that telescope will look like. It'll be 25 meters across, but it's made out of 7 individual 8.4 meter mirrors. You can see, to really get an appreciation of how big even 8.4 meters is, which is close to the size of the biggest telescopes in the world today, you have to take 9 big steps across your room and realize that that's the size of one of these mirrors. 25 meters is really big, right? 82 feet across. So Dan originally started thinking about a near-infrared spectrograph for the Giant Magellan Telescope, and I became involved when he asked me to think about what exciting science that this instrument could do on such a big telescope. And so I started working on that science case in 2009. But then 5 or 6 years ago, we realized that it would be really great to have this instrument on one of our current telescopes before the GMT was ready for it. And that's because we could use it to do great science, even on a smaller telescope. And I'll show you that in a couple of minutes. But also that would enable us to get all the bugs out and really understand how to use it really well before it went to the bigger telescope, and we'd really be able to hit the ground running. So MagNIFIES is the implementation of the spectrograph concept for Carnegie's current Magellan Telescope. one of them anyway. They're 6.5 meters across, which is, still pretty big. Okay, so this is a near infrared spectrograph. So let me explain all of those terms, starting with near infrared. So we're used to thinking about visible light, but of course, light covers a much wider range of wavelengths, from very short wavelengths, starting with those that are just bluer than blue, or the ultraviolet, the light that gives us sunburn, and then into X-rays. And it includes light that's redder than red, or the infrared. And so here's a picture of me in the infrared. The infrared is great at looking at things that are warm. And so you can see I'm glowing yellow here. White is hot in this image. So I'm glowing very strongly in the infrared. And it's also really good at looking at places that visible light doesn't penetrate. So let me show you that. Here's a picture of my teenager wearing his Earth and Planets Laboratory t-shirt. And here's what he looks like in the infrared. He's glowing quite strongly. In this case, red temperatures are about 32 degrees. This is centigrade. Blue temperatures are about 20 degrees, room temperature. And you can cover up my teenager with a plastic bag. I just want to assure everyone that no teenagers were hurt in the making of this slide. The plastic bag is not over his head. He's just holding it up. And you can see that visible light doesn't get through this. It's just an ordinary trash bag that I got from Costco. But if you look at him in the infrared, you can just see the outline of that trash bag. That infrared light from him is still coming through quite strongly. He's a little bit fainter. We've knocked about 5 degrees off of the temperature that we're able to see through it. But we can certainly see him and his shape and important features about him through this obscuration. So that's one of the reasons that we use the infrared. We use it in areas that are very dusty, such as newborn stars and the disks that surround them that could be making planets. Just for fun, I thought I'd also show you a picture of the Magellan Telescope in the infrared that I took a few years ago. Here you can see the nice temperate areas that the astronomers stay in are warm. The ground is warm because it's heated up during the day, but the telescope is staying nice and cool as the nighttime temperature will be, so that we can make good observations. That's one of the reasons that our telescope works so well, is it keeps the telescope nice and cool during the daytime while everything around it heats up. So that's the power of the near infrared. But let me also tell you about the power of spectroscopy. So spectroscopy is just a fancy way of saying that we're breaking light up into its component colors. And you've probably all seen a rainbow, or you've seen a prism that breaks light that's coming into it up into colors, so that you can see them individually. So when I show you spectra, I'm showing you how much of each color is coming through. So this is a little tiny portion of the infrared spectrum. We usually talk about wavelength in the infrared in microns. We usually talk about wavelengths in the visible in terms of a different unit, like nanometers. But microns is 0.5 microns is 500 nanometers. So 500 nanometers is the center of what we can see in our visual range. But out here, we're in the near infrared. So this is a model spectrum of a hot exoplanet. And these are all individual lines from a molecule that we know and love, water. And each of these spectral lines is like a fingerprint of water that could be in the atmosphere of a hot exoplanet. And so this particular pattern is made by water and water only. And if you see it, you would know that water was there. But you can see that we have to break this tiny bit of spectrum up into a lot of individual defined subunits of wavelength before we're able to see each one of these lines. So in this little tiny part of the spectrum that I'm showing you are about 1,500 individual pixels of wavelength coverage. And if we don't break it up as finely, what you get is something like the yellow line. So this is what the highest resolution, most capable spectrograph on the James Webb Space Telescope that NASA will launch later this year can do. And you can see, you can still pick up individual water lines, but they start to blend together when there are a lot of them. And then this blue line is the spectral resolution of the workhorse spectrograph on the James Webb Space Telescope that will be used for exoplanets. And as you can see, you can still detect that there's water, so there's a dip here, but you can't see any of the individual lines. And so you've lost a lot of information that each of these lines and the fingerprint carries as you go to lower and lower spectral resolution. So I like to say a picture may be worth 1,000 words, but if you can take a picture at 200 to 250,000 different wavelengths, that's an amazing number of pictures. And that's what MagNIFIES will be able to do, make something like 200,000 different pixels of wavelength information. So that's important because it takes a lot of different wavelengths to fully understand what's going on with stars, with the disks around them, and with exoplanet atmospheres. So here's an illustration going back to that star that I talked about before, TW Hydra, which is the nearest example we have of a disk that's probably still making giant planets. And so in blue, you can see the spectrum, now at a pretty low resolution, taken of that star, all the way from 1 microns to 5 microns. And very importantly, there are many, many diagnostics in this spectrum that if you were able to focus on them in much more detail with much higher spectral resolution, you'd be able to find out a lot more about what's going on. So you don't see it in the low resolution spectrum, but if you zoom in over here at 4.8 microns, you see gas from carbon monoxide in the disk. If you zoom in here around 3 microns, you see water and its dissociation product, OH. And around 3.3 microns, you can even see a tiny bit of methane in the disk. So these are all the gases that could be going into the planets that are currently forming in this disk. And we can only learn about them by covering a broad range of infrared wavelengths. At the same time, we're learning a lot about the star. The fact that it has so much of this emission in this part of the spectrum tells you that it's accreting gas from the disk still, and tells you about how the gas and the star are interacting. We can also measure the star's magnetic field. We can tell what temperature it is. We can see if there's a wind coming off the star, but we can only do that if we can cover a large part of the infrared spectrum all at once. So that's what MagNIFIES is designed to do, to cover all the way from 1.08 to 5.3 microns. Now you'll notice there are some gaps in the spectra. There's no data here, nor here, nor here. And those are due to absorption in the Earth's atmosphere. So very little infrared light comes to us through the Earth's atmosphere. That's why we make space telescopes, among other reasons, so we can see in those regions that are obscured by the Earth's atmosphere. But as you can see, most of the infrared spectrum does get through. Back in the old days of infrared astronomy, when people were just starting to look at the sky in the infrared, they were trying to get as much light as possible. Their detectors weren't very good. And so they designed filters that would capture all the light between the areas where the atmosphere was opaque. And as they discovered windows where the atmosphere was transparent, they lettered them in the order in which they found them, which is why, if you're wondering, J, H, and K are out of order, thus permanently confusing my knowledge of the English alphabet, because I usually think about infrared windows. So why is MagNIFY special then? Well, because it covers the entire infrared from 1.08 to 5 microns with all those important molecules that we can, and atoms that we can learn about in the near infrared. And it covers it in incredibly fine wavelength detail, or what we call high resolution. So that tells you about a lot of the parts of this somewhat tortured acronym that I made up. So it's the Magellan, okay, it's going to go on Magellan and then Giant Magellan. Near infrared, we talked about why that's important. 5 band, that's because we labeled these J, H, K, L, and M. Those are the 5 bands. And it's a spectrograph. And in a minute, I'm going to talk about the immersion, grating, and the efficient part of the acronym. So if we can cover a lot of wavelengths at once, that's the first thing that makes this an efficient spectrograph. So there's a precursor instrument to MagNIFIES called IGRINS that was built by Korea and the University of Texas and is currently operating on the Gemini Observatory. And it covers just 2 of these wavelength regions. So here I'm labeling them with those letters that I showed you before, and also by the wavelength in microns that are covered by each one. So this predecessor instrument, and this is an actual spectrum from it, is just this one little part of the near infrared spectrum that MagNIFIES will cover. And in order to fit a lot of spectrum onto one detector, so we have 2,000 by 2,000 pixels. So we're going to have 6 of these detectors in total. So that's about a 25 megapixel array of detectors. We take and we split up the wavelengths. So we start we get them in chunks. So lower wavelengths are at the upper left. So this might start at 1.45 microns and go to 1.48 microns. Then the next chunk will start at 1.48 and go to 1.51, et cetera, all the way down until you get the final 1.8 to 1.83 region in this full image. But now we do this 6 times. So that adds efficiency because we only have to take one exposure and we get all of these wavelengths at the same time, each on their own detectors. You notice actually we've split up what I call the L band. So the L band, if you noticed on here, is very wide, right? More than twice as wide as the other bands. And so we can't fit it all on one detector. So we split it up into 2. So the other thing that makes MagNIFIES incredibly efficient is that we take as much light as possible from the sky and send it through to the spectrograph. And I know that sounds obvious, but it's actually really challenging to do. And MagNIFIES is going to do it better than any instrument has ever done it before. So this is a plot that shows how much signal or signal to noise you get on a source as a function of how bright that source is. So fainter sources are over here and brighter sources are over here. So if we want to study faint things in the galaxy, we want to be looking at faint objects with a lot of signal, right? So every instrument in the world would love to be in this upper left corner of this plot, getting a lot of signal from a faint object. This is where instruments actually are. So these are 4 currently, the current generation of infrared spectrometers on the ground. And MagNIFIES is better than almost all of them, almost all of the time. So just choose one of the bands to look at. Let's look at H band here in pink. MagNIFIES is way above and to the left of any of these other pink points that represent what can currently be done. So this is a huge improvement in sensitivity, about a factor of 6 compared to the best current instruments on the ground. So those 2 things combine to give a huge improvement in terms of how fast you can make an observation of something in the universe. So just to make this clear, say you wanted to cover this whole wavelength range with the current instrument that's on the European Very Large Telescope, not too far away in Chile from where our Las Campanas Observatory is. Well, it only covers half of the band at once. So you have to take 12 individual images with that, or 12 individual spectra with that instrument to cover what MagNIFIES does at once, all at once. But then remember, I also said MagNIFIES is so much more sensitive. So you can't just do this once with the current instruments. You have to keep going. You have to do it again, and a 3rd time, and a 4th time, and even a 5th time to build up to see the same faint object that MagNIFIES could do in just one image, getting all of that spectrum all at once. And so that makes MagNIFIES up to 50 times faster than existing instruments. So how have we been able to do this? That's an amazing improvement in terms of the current state of the art. Well, at the heart of this instrument is the grating. That's what separates the light into its component wavelengths, into its component colors. And these are really cool gratings, which I have to just spend a minute telling you about because it's such a neat technology that was developed by Dan Jaffe at the University of Texas in his lab. So if you take pure silicon, and pure silicon is a really important product for the semiconductor industry, right? The computers that I'm using to display this and you're using to watch this all depend on chips built around silicon. So there's a big industry already that exists in making very pure silicon crystals that people can use for the semiconductor industry. So you can take one of those pure boules of silicon and you can etch it, actually the same way, again, that the semiconductor industry etches silicon. But silicon is a crystal. And so if you cover up certain parts on the surface and then etch between them, it will preferentially etch along the crystal lattice of silicon. And that makes a series of grooves, which is exactly what a diffraction grating or a grating of any kind is. So, and in fact, it's exactly why, hopefully you can see that there's a bit of a rainbow that's being created here, if you're old enough to remember what these objects, these DVDs or CDs are. They're written with many different individual grooves. And in the visible, that will create a rainbow. And the same thing happens when you hit the grooves in this silicon immersion grating with infrared light. Now notice silicon is pretty dark in these images, right? Silicon is opaque in the visible, but as you already saw with my son in the plastic bag, you can be opaque in the visible and transparent in the infrared. And it's called an immersion grating because the light goes in, so it's immersed in the silicon before it hits the grooves and then reflects back off of them to come back out again. And that means that the resolution of this grating, how finely it can break up wavelengths, is increased by the index of refraction of silicon, which is very high, 3.4. So that enables you to make a very small grating. So the gratings for magnifies are only 90 millimeters in size for the shorter wavelengths and 125 millimeters for the longer wavelengths. So you can make them small, but you can still get a very high wavelength resolution. So that's at the heart of this instrument, and we need 6 of them, one for each individual spectrograph that feeds each of those detectors that I showed you on the last slide. So here's what a layout of the optics look like. So there are basically 6 very similar spectrographs. The light comes in a single place, and then it gets sent out to each independent spectrograph based on what wavelengths each one can cover. And when it goes into the individual spectrograph, it hits the grating, it gets separated into its component wavelengths, and then it gets focused down on an infrared detector to form the spectra that I showed you before. I should say there's also a second grating which spreads out all those individual chunks of spectrum on the detector. And because the gratings are small, we can fit this in a pretty compact size. So you can see the dimensions of the final enclosure are pretty human size, 1.4 meters. I'll show you that to scale in a minute. So to work in the infrared, we have to place the optics in an enclosure that can keep them cold. So all these optics and the gratings will be taken down to a temperature of about 70 Kelvin. And the detectors actually work best even colder, so they'll be at 37 Kelvin. And it's all in vacuum to prevent any thermal, air from conducting heat around, and to prevent any condensation, any gases from our atmosphere from condensing onto these very cold optics. So this efficient design lets us put it in a compact size. So here's a rendering of our current Magellan 6.5 meter telescope. So here's the primary mirror. That's what 6.5 meters across. The light comes in and hits the primary, goes up to a secondary mirror up here. You can see why it's named the secondary, because it's the second. Comes down to a tertiary mirror, and the tertiary can actually rotate to choose where it's going to send the light. So we can send it to magnifies, currently mounted over here, or an instrument mounted, bolted onto the side of the telescope, or over to another platform. So this platform has a little elevator. This elevator looks like it's suspended in midair, but has a little elevator that comes up so you can roll instruments onto the platform. So there's magnifies, and notice the human standing there on the platform. That human's supposed to be me, but actually the engineer who made this obviously thought I look bigger than I really am, which I guess is good. So it's wishful thinking on my part, because I look like I'm 5'8" in this picture, but I'm actually only 5'5" on a good day. So, but you can see magnifies doesn't even take up all the room that's available to it on this platform. It'll be pretty easy to get on and off the telescope and for humans to assemble and work with. So what do I want to do when we get this on the observatory? Well, the first thing I want to do is study disks like the ones that I showed you before. And the second thing I want to do is a survey of modern exoplanets and young exoplanets to find out what they're made out of. So I showed you a little piece of a spectrum before that is, from a hot Jupiter exoplanet, or a model for a hot Jupiter exoplanet. But now I wanted to show you how that spectrum is actually composed of lines that come from different molecules. So each of these molecules has its own fingerprint in the infrared. That's its pattern of lines that it produces. And so in this particular model, we have water, we have carbon monoxide, we have methane, and we have carbon dioxide. And magnifies, because it covers such a wide wavelength range, and here I'm only showing you the 3 to 5 micron part, but there are also parts of fingerprints of these molecules that can be observed at the shorter wavelengths. We can search simultaneously for these molecules and more. Also for molecular oxygen, that has more like 1 to 1.2 microns is a region to look for it, but also molecules with nitrogen and the molecules with sulfur in them. And so we can search for all of these at once. We don't have to choose. And because we know so little about the atmospheres of exoplanets, not having to choose is really important, because if you don't know exactly what you're looking for, you just want to take in as much light as possible and see what's there. And so that's why the first survey we would do is really a large scale reconnaissance of a lot of different planets. There's maybe a dozen for which we have compositional information right now, and we would want to do them in much greater detail. And the way we do that is we actually watch the planet as it goes around its star. And so the planet has a velocity that shifts those lines by the Doppler method, Doppler shift. And so you can actually trace out the orbit of the planet as it moves around the star. The planet doesn't have to go directly behind or directly in front of the star in order for us to see it this way, because we're seeing the hot day side of, in this particular case, a planet that's quite warm and quite close to its star. And these are real data that just came out in a paper yesterday by Michael Line, who's a professor at ASU. And he actually was able to trace a range of the orbit of that planet by tracking the planet's velocity. And by making a model spectrum, he was able to detect carbon monoxide and water vapor simultaneously in the atmosphere of this planet. And that uses IGRINS, which is this predecessor kind of prototype instrument for MagNIFIES. So this has also been done for one very young planet. So this is an example of that same technique, stacking up all the velocities and detecting a planet, this time just in carbon monoxide, but this planet is only 3 million years old. So this planet is probably a billion years old or so, like more similar to the sun and its planets, and this one is extremely young. So with MagNIFIES and the increased speed that we'll have in observing planets, we'll be able to do a much larger sample and trace them all the way from very young planets to old planets like the ones in our solar system. So what's next? Why don't we have it already? So this coming year, we will be receiving cameras and a test detector thanks to that seed funding from the Heisen-Simons Foundation, and we'll be putting in a proposal to the National Science Foundation for the rest of the money that we need to complete the instrument. And we think that we can do that in 4 to 5 years. And so we would have delivery to Magellan in something like the 2026 or 2027 timeframe. And meanwhile, construction on the Giant Magellan Telescope is ongoing. And so at some point when that telescope is complete, maybe around, and has its adaptive optics system in place, so maybe around 2032, MagNIFIES will be reconfigured and become GMT-nears and be delivered to the GMT to do even more amazing science on a much larger swath of the galaxy. So I'm happy to take everyone's questions now. I will just leave you for a brief second with this beautiful view of the sky over the Magellan Observatory. You can see why it is we're so excited to do astronomy from Las Campanas Observatory, because we are privileged to see these gorgeous night skies. Here, of course, is the Milky Way stretched from nearly horizon to horizon. This happened to be taken during a lunar eclipse. So I will stop sharing my screen and I will be happy to take your questions now.
Great. Thank you so much, Alycia. That was a fantastic talk. We do have a bunch of questions, and so I'll start with them and I'll interject some of my own as well. I want to remind people that if they have questions, they should put them into essentially the Q&A function in their Zoom, because we'll take as many questions as we can in the time that we have. So let me start on the science side. You started by talking about why you got into this business to build instruments. So let me ask a question. Jeff Greenspan has asked a lot of questions, that some of them related, and with the materials that you can observe. So let's consider the protoplanet, the early disk that you're observing. And the question is, do different components, so you have gas, you've got dust, you've got different things that are in that. Do they disperse at different rates, and how does this impact the outcome of what a planet might eventually turn out to be?
Right, that is exactly the question that I want to answer. So, the gas could have different compositions in different places in the disk. So for example, if you're too close to the star, ice is evaporated and forms water. And if you're too close to the surface of the disk, ultraviolet and X-rays from the central star and also from stars around it can hit the top of the disk and break water up into OH. So depending on where you are in the disk, you might have access to more water as part of your composition. If you're a forming planet, you might have access to more carbonaceous materials like carbon monoxide. If we were able to form a disk that didn't have a lot of oxygen, you might not have much water or carbon monoxide, but you might have a lot of methane, and you might form a kind of tarry, gunky planet made of soot. So the composition in the different places in the disk matters a lot. And one of the powers of high resolution infrared spectroscopy that I didn't talk about is the ability to measure where in a disk the different gases are coming from. So we look for the fingerprint of a particular gas, like water, and we measure its velocity with respect to the central star. And the closer gas is to the star, the faster it'll be whipping around, just like Earth moves around the sun faster than Jupiter. If the gas is out further, like the orbit of Jupiter, it'll be moving slower. And that shows up as a change in the wavelength of those gas lines in our spectrum. And so we're able to translate spectroscopy into where in the disk a gas is coming from, which is really one of the powers of spectroscopy.
Thanks. There's a related question, which I think you already answered, which is what are the mechanisms that are responsible for this dispersal, the variation of components in a disk? So you have, each planet, even in our own solar system, are quite different. So what's responsible for that kind of a variation?
Right. And so one thing, for example, that we think happens in disks is that dust grains, which are there, are constantly colliding with each other and growing. So you get like the dust bunnies that grow under your bed, or at least under my bed. The dust bunnies grow and then they hit another dust bunny and they get compacted and eventually they build up. But if you're in a very cold but water-rich part of the disk, then water will condense onto those dust grains like it does onto your car window on a cold day, and you'll now get a dust grain covered in ice. And now that dust grain covered in ice might move toward the central star, where it could either get incorporated into planets along the way or eventually gets so warm that it releases that water into the inner part of the disk. And so there's a lot of motion. There's a temperature changes in the disk from hotter in the center to cooler in the outer parts. And there are motions of gas and dust within the disk that can both change where certain molecules appear in the disk. And so here's a really cool thing that I think would be fun to study. So we know that young stars, when they're grabbing or accreting gas from their disks, flare. Sometimes they flare even without gas coming onto them, but the gas accretion can cause a big increase in luminosity. And that means that all of a sudden you're illuminating the disk with a lot more light and it gets hotter. And so if there's a region where ice turns to water in the disk and the star suddenly flares, well, you might suddenly get a lot more water in one place in the disk and the ice will be further out. So we might be able to actually watch those kinds of things happen in real time by taking many spectra over time with an instrument like MagNIFIES.
That's great. Phil Hopkins has an interesting question. So what elements are you not able to document or measure, and what effect might that have on your ability to really understand what this disk looks like or feels like? Right.
So we tend to concentrate on a few important elements. Because we don't have access to them all. Almost all elements and all molecules will have these transitions, these lines in the infrared. But the problem is that as you get to rarer and rarer elements, those transitions get harder and harder and harder to see. And so the first things we detect are always the most common, so carbon monoxide and water. And they're common because carbon and oxygen, after hydrogen and helium, are the most common elements in the disk. And so they're both common, and it gives us a really important constraint, which is the carbon to oxygen ratio. We like to think the Earth might be pretty different if it had a different carbon to oxygen ratio than we have, right? If we didn't have enough oxygen to go into water, for example. So those are the things that we see first are the things that are really common. Interestingly, there's one incredibly common element that is very hard to see, and that's hydrogen. Because even though it's the most abundant element, in most of the disk, the hydrogen is bonded to another hydrogen. So you just have this very symmetric molecular hydrogen. And it doesn't have, some symmetric molecules don't have strong transitions. So this is also true of molecular nitrogen, which is a lot of it is in the Earth's atmosphere, right? We don't have very much access to those very symmetric molecules. So it's very hard to actually see the bulk of the mass in the disk.
Okay. So, I mean, in a minute, I'll come to asking you to compare ground-based versus space-based, where you can start talking about rotational modes of H2 or whatever, but a few more questions relative to protoplanetary disks. And a really interesting question here, which is, can you compare a protoplanetary disk, say around a nearby star or our own solar system, to say the rings of Saturn? And are those the same thing, or are they entirely different?
Well, they're similar in the sense that all rings are flattened structures, like looking at, the CD is not a sphere, right? It's flat. So in that sense, disks around like the rings of Saturn and the disk around a star are similar. Where they differ quite a lot is the amount of gas. So in those original disks around stars, the bulk of the mass, maybe 100 or even 200 times as much mass is in gas as is in dust. And so you can form things like giant planets like Jupiter out of those disks, where Saturn's rings are almost entirely made of ice and a little bit of rock.
So great. So I do want to come back to your very beginning when you started talking about your sun, because it's related to these questions here in the Earth's atmosphere. First, I want to say I was fortunate enough to meet your son down in the Atacama Desert when we were all down there 2.5 years ago for a total solar eclipse. He's a really wonderful person. Glad he's excited by science. Hoping you will get him into science. I also want to say, by the way, as president, I was delighted to hear that nobody was injured in doing those measurements. And I also know that your parents are watching too, and I'm sure they're even more delighted to know that their grandson is safe and that their daughter isn't exposing their son to something dangerous. Okay, I just wanted to say that. So, the question of the atmosphere, if you're on Earth, what are the limiting features of the atmosphere, right? It's not just that they absorb. What are the things like fluctuations that lead you to making modifications to Magnify? So maybe talk a little bit about fluctuations and corrections due to the atmosphere, but also absorption and how it does affect your ability to see clearly. And then we'll go to the comparisons with space telescopes.
Right. So I already showed you that there are places that the Earth's atmosphere is not transparent. It's opaque. We can get around that from the ground to a certain extent by choosing objects that are moving in such a way that their lines are Doppler shifted out of the regions where the Earth's atmosphere is opaque. So we can overcome that to a certain extent, although not completely. In terms of the fluctuations, right, the stars twinkle, and they do that because of variations in the Earth's atmosphere that are constantly changing with time. And so that causes us not to usually be able to take advantage of the full size of our telescopes to see the kind of detail in astronomical objects that we would be able to see. So the technique that we employ from the ground to overcome that effect of the Earth's atmosphere in blurring objects is called adaptive optics. And what we do is we use another star or a laser to make an artificial star and observe that fluctuations coming from that reference star. And then very quickly, 1,000 times a second, maybe even 2,000 times a second, we deform a mirror exactly opposite to the deformation that the atmosphere is making. And in that way, we can correct the light before it hits the instrument. And at Magellan, this is currently done with a secondary mirror that does that deformation in what's called the Magellan Adaptive Optics Project. And that's exactly what will be done on the Giant Magellan Telescope. So there will actually be 7 of those individual adaptive mirrors, one for each of the primary mirrors, and they will do that correction before the light gets to the infrared spectrograph. And that has a couple of advantages. One is that we are able to do even slightly higher spectral resolution when we move to the GMT, because we're concentrating the light in an even smaller patch. But maybe more importantly, what it lets us do is measure how the velocity changes with location on the sky, or how the spectrum changes with location on the sky. So we could actually look at a disk and not only use the velocity information to say where the gases are, but actually use their location on the sky, because GMT is correcting that for us to say where the different gases are located.
And I would add that these adaptive optics features are of the most important thing one of the most important new things in this giant telescope. It's not just big, it also is able to correct for these kinds of atmospheric variations. So it's very exciting and will help you a great deal, I'm sure. We had several questions. This will come up often when you're talking about expensive big instruments. But the first question, and there's a few related questions to this. One is, what is the difference between, say, a JW? Everyone has heard about the James Webb. It's going up in December. It's a very exciting event for NASA, for all of us. I mean, some of us already have beam time or observation time on it, so we're all very excited by it. But what are the differences between what you can do, say, in a 6.5 or even 24-meter telescope on Earth versus what we're going to get in JWST?
Right, that's a good question, and they're complementary. So JWST is a 6.5-meter telescope, so it's the same size as Magellan. So that's much smaller than the Giant Magellan Telescope will be. Because as big and expensive as things are on the ground, they're much, much, much more expensive when you move them to space. So you can't do everything with a space telescope. So the fundamental capabilities of the James Webb Space Telescope were set 20 years ago. And among other things, it does not have this very high spectral resolution. So I showed you in one of my early slides how you could see those individual fingerprint water lines and what they would look like if you instead were looking at them with the James Webb Space Telescope at lower spectral resolution, less fine detail. And one of the implications for that is that if the lines are weak, as they very well might be in, say, terrestrial mass planets that have a lot of clouds, or super Earth planets that have a lot of clouds, those lines will be essentially impossible to detect with low resolution spectroscopy, because the clouds block most of the atmosphere from being visible to you. And so I really think the only hope we're going to have for looking at cloudy atmospheres is this very high resolution spectroscopy, where we can see each of the individual lines and we get our signal to noise by adding the signal from all of those lines together. So that's one example. We can also take advantage of the velocity information in both disks to understand where the gases are coming from, but also the planets as they move around their stars. We can only do that because of high spectral resolution. And so James Webb won't be able to do that. So there are many fabulous things that James Webb will be able to do, including observing in those regions that we can't see, but also because it's very cold. Like, we live in a bath of infrared photons here, right? That's why I look hot. I'm probably looking really hot right now if I turned on my infrared camera, because I'm all jazzed up about this talk. But you know, we live in a bath of infrared photons we just can't get away from. You saw that picture of the observatory with the hot ground. Like, James Webb is going to be in space where it's cold, and so it can be much more sensitive than a telescope we can build on the ground. So for looking at really faint things, James Webb will be unparalleled. But for looking at things at high spectral resolution, you know, first Magellan and then the Giant Magellan Telescope will be really phenomenal.
That's a good answer. You know, people are always looking to this, and I will point out that the James Webb will be fantastic. It'll be, the thing is, it'll be about 10 times more expensive than the Magellan telescopes on Earth, roughly, maybe more. Well, but it's a very important project for the US. However, you know, there is this bigger question, and it's really more of a personal statement, Alycia, which is, you know, why do you think there's such value in investing, you know, billions of dollars in these important science experiments? It's a general question you could ask for any science, but in particular for astronomy and your interest in understanding the universe.
It is a general question. You know, if I could spend my money and magically make COVID go away, you know, it's hard to say I wouldn't do that. But, you know, to me, astronomy is one of the fundamental sciences that fires the human imagination. And I think it would be a sad state of affairs for people, Americans, but just people in general, if we didn't get to satisfy our innate human curiosity about the universe that we live in. If we didn't get to answer the question, are we alone? Or how special are we? How unique is the solar system? Those are age-old questions that I just can't imagine anyone, or especially anyone under the age of 15, who isn't interested in those questions. Yeah. So to me, we always have to take the next step in doing a little bit better than we've done before. And you know, the giant telescopes, there's no substitute for the beautiful images behind the adaptive optics system, so correcting for the Earth's atmosphere, that the Giant Magellan Telescope will be able to make. And that will be phenomenal. And I think it will, hopefully some of those will be of individual planets that will then go and point magnifies at and take spectra of. And I think that it has the potential to excite a lot of imaginations, not just mine.
Yeah, and I think that's a great answer. I mean, I totally agree that it's almost a human nature to try to explore new things, and for us to understand how the universe started, what the elements are made of, if life exists on other planets, are such fundamentally important questions. It's not just you and I are not just a bunch of scientists talking about it. I do think there's broader human interest, and it is true. I mean, you can ask, why are we spending so much on this and not equity in the world? And that's a good question. However, this is a tiny fraction of what we're spending on many other things in this country. So that's something. I'm going to come back to
the problems are ones like we know how to solve, like technologically, right. We know how to build this instrument. We can do it. And there's a lot of things that aren't so easy.
Yeah, agreed. Societal issues are much harder in some ways, and I totally agree with that. Like a little more, we have time for a few more questions. I'm going to dig a little bit down into the technical detail now on the science. And we had a good question about isotopes. As you well know, isotopes are a great way to measure history, right? We do that on Earth with isotope measurements in the Earth, deep in the Earth. And of course, there are many isotopes that are out there in these disks you're talking about. Can you detect different isotopes, and can you use them to do things like histograms of disks and learn about the history?
I really hope so. I mean, absolutely, it should be possible. So isotopes are atoms that have the same number of protons, but different numbers of neutrons. And so the most common one is that we might think of as deuterium. So that's just hydrogen plus an extra neutron. And so, for example, you can have HO, right, water, as we know and love it, H2O, or you could have HDO, where you substitute a deuterium for one of those hydrogen atoms. And that subtly changes the spectroscopic fingerprint of the molecule of water compared to HDO. And so you can do that with any other molecule that I showed you. You could take carbon and oxygen, you could substitute carbon 13, or you could substitute oxygen 17. And so there are lots of possible combinations. So absolutely, we can detect them. They all have signatures in the infrared, the same way as the main molecules do. They are, of course, much rarer, and they therefore are harder to detect, as I said in the answer to the other question before. As things get rarer, their lines get weaker. So this is definitely an experiment we're going to do. There are people who have done models that suggest we should be able to detect some of those. We call them isotopologues. That's a molecule where you substituted in an isotope. And the first one we would probably try is some carbon monoxide isotopologue. But they've already been detected in the cold outer reaches of disks. You may have heard of the ALMA telescope. That's the one that we were visiting in the Atacama a couple of years ago. And so they have definitely been detected in disks using ALMA. What we want to do is detect the ones that can only be detected in the infrared and in the central part of disks, not just the outer parts.
That's really, that's cool. There are many more questions. Unfortunately, we can't get to all of them, but I do want to ask a few more questions. So speaking about history, we're now up to over 4,000 planets we've identified. So that means, maybe somewhat less solar planetary systems. Do we have a good sense now at how fast planets clean up the disk and finish their production? And we get to a point where we're now, I'm not talking about atmospheres now, I'm just talking about sucking up all this beautiful dust and rocks, et cetera, in the disks. When do they disappear? How fast does that planet really suck up all that stuff? And become
that's been one of the surprises of my work from 20 years ago and a lot of other people's work, is that they suck up the disks amazingly fast. Well, there's kind of three ways you can imagine a disk goes away. One of which is it creates planets. One of which is that the disk falls onto the central star and adds to its mass. And the other is that the disk gets blown away somehow. So all three of those things happen. One of the things we want to understand is the relative contributions of those in the late stages of planet formation. But one thing that we learned from all of our studies is that happens really fast, within a few million years, and certainly by 10 or 20 million years after the star is formed, the gas is gone and most of the small dust grains are gone along with it, especially in the inner disk. So to make big planets like Jupiter has to happen really fast. And that's what's motivated a lot of really interesting theoretical work on how to make giant planets quickly, including by my colleague here at EPL, Alan Boss. And it's really made us reevaluate our planet formation theories in light of the fact that observationally disks go away quite quickly.
Okay, I'm going to ask one more somewhat technical question, then we're going to move to some final questions I'd like to ask. What are the odds that we'll, I mean, so all the planets we've seen so far, of course, are in nearby stars. So what's the most furthest planet we might be able to observe? Is it going to ever be possible? I mean, just give us a sense of the limitations.
Well, so there was an announcement a few days ago about the first planet discovered in another galaxy.
Yes, we saw
that. So
that.
if that turns out to be right, it was discovered because it is around a X-ray emitting star, and the X-rays went away for a short time. They were blocked, and the paper hypothesizes that that's from a planet. So if that's right, there are actually ways to detect planets even outside the Milky Way galaxy.
Yeah.
I'm most interested in the ones that are close because they're the brightest. And so they're the ones that we're going to be able to learn the most about.
Yeah. I might also add that if there's an X-ray emitting star, it's probably not likely that there'll be any life on that planet.
It was a stellar system very unlike ours that they found this planet around.
Yeah, that's great. So let me ask a question that I'm sure everyone's interested in, Alycia. Why, maybe say a little bit about why you got interested. We have a lot of people listening, maybe a lot of people with kids, maybe young daughters who might be thinking one day about science. Why is it that, obviously you're very excited about what you're doing. You couldn't imagine doing anything else, but maybe you can say a little bit about how you got into this field.
I think I just am the kid who never grew up. I was always interested in astronomy, and I don't know why other people stopped being interested in astronomy, but I never did. I still have the little telescope that I bought when I was 13, with, to be fair, contributions from my parents as well. And, I have always also liked tinkering with things. I've always liked instrumentation. I did some instrumentation as a graduate student. And every time I took a path in my education, I realized that I was happiest with the path if it involved doing some observational astronomy work. I really love going to the telescope, hearing the motors in the background, feeling like I'm part of the observations. It's been great to be able to observe remotely for the last year and a half from my basement, and it has some advantages in terms of not having to fly to Chile. But I really miss that experience of being with the equipment and getting to know it well, and in this case, now hoping to improve it. So I don't have a good answer otherwise to why people should be interested in astronomy, other than it's a part of my innate curiosity.
Yeah, I mean, actually, that's why I'm a condensed matter physicist, but I got into physics because of astronomy as well as a kid. Same probably way you did.
That's a gateway drug. Yeah.
It's just great. So I think, we've had so many great questions. Unfortunately, I apologize, we can't answer them all. We will try to answer additional questions that have come up in the Q&A. We're at the end of our time. I think Alycia wants to go back and start rebuilding the instrument so that she can get it on the sky. And I really want to thank you, Alycia, for a wonderful talk, and the question and answer period. I think illuminated, no pun intended, illuminated a lot of the science. I know there's a lot of questions that many would love, but maybe we'll get another chance to visit with you in another year or two. And I also want to thank the audience. This is, as always, we have great audiences, but this in particular, really great questions. Thank you so much for coming, and we'll look forward to seeing you again in the coming months.